Good morning, dear students. Welcome to another session of microwave and antenna. So in previous session, we discussed regarding radiation intensity, radiation patterns. Then we discussed regarding problems pertaining to the beam area or beam solid angle using the exact equation and using the approximate equation. Now, continuing with where we had stopped yesterday, that is, we'll continue with what is meant by beam efficiency. So, in the previous discussion, we came across the term the beam solid angle or the beam area. So, whenever we are considering the beam area, right, for example, if I have to represent the radiation pattern. So if I have to represent radiation patterns, say for example, I'll take this example. So when I consider this radiation pattern, right, what happens is if I have another antenna which is placed over here, how this antenna will observe is it will that is how large this radiation will be appearing to this antenna will be based on the beam solid angle. So whenever we are considering the beam solid angle, right, what happens is you observe that if I am standing at this end, I'll be actually looking at the main beam in this case, but along with this, what is happening is you have even the side lobe. You have the main lobe and even you have the side lobes which are present. So therefore, what happens is when we consider the overall beam area, we can say that it is the addition of the main beam area which is due to the main lobe and the beam area due to the minor lobes. So it is a combination of these two. It is beam area due to the minor lobe added with the beam area due to the major lobes. So this is what I can specify when we consider the overall beam solid angle. So now based on this, I can define few efficiencies, that is the main beam efficiency. So the main beam efficiency is given by the beam area which is subtended by the main lobe divided the overall beam area. Overall beam area. So this ratio gives me what is called as beam efficiency. Now, similarly, we can identify what we call as stray factor. Stray factor is relevant to the beam area which is subtended due to the minor lobe to the overall beam area which is subtended by the antenna. So it is given by this ratio. So this is termed as stray factor. And when I add both the factors, right, that is the beam efficiency and stray factor, its total will lead to 1. So this is with respect to beam efficiency. Now, next concept what we have is directivity and gain. So directivity in short can be defined as the ratio of average power density, ratio of maximum power density to ratio of the average power density. So we can define the directivity as the ratio of maximum power density to average power density. And if we observe, directivity is always greater than equal to 1. Directivity cannot have a value which is less than 1. Now let us see what is actually the average value of power density. If we know, say, the normalized power pattern, or if we know the power pattern, how we can identify the average power value. So here we have the equation for average power density. So now how did I get this? So if you remember or if you identify, Suppose you have a sequence of numbers in a discrete form. You have a sequence of numbers. You have one, two, three, some numbers are there. Now, say there are n numbers over here. Now, if you want to identify the average of this, what you do, you take summation of all these values. You take summation of all these values. That is, you add these 1 plus 2 plus 3 plus so on up to n numbers. And if I want the average, right, what I do is I divide it by the number of elements which are present over here. So this is in terms of discrete. But when you have in terms of continuous, right, what you do is summation will be replaced with integration. This is for discrete terms, but when it comes to continuation continuous terms, right, then we have to use the integration. So integration of say some element, say x of t dt, it is nothing but you are adding all the elements related to x of t. So that is what you are doing. Suppose you have a sine wave. Suppose you have a sine wave and I want to identify what is the average value. So let me specify this as s of t and this is t. Suppose I want to find what is the average value of all these points. So in order to do that, first I should sum all these points from, say, I'll consider one cycle of this. So I'll consider one cycle because after this again it is repetition. So I want to identify what is the average of this. So first I have to sum all these points. So if I have to sum it, what I do is I take integration of this function s of t with respect to t. So now so this will give me the overall sum of all the points, but I have to identify the average, then I have to divide it by some factor. So whenever we consider in such cases, right, in this case, what it implies is, so you're summing it from what, 0 to pi and then pi to 2 pi. So you are summing all the elements from 0 to 2 pi. You are taking all the values of these and you are summing these points. So we divide this by the factor of 2 pi. This will give me the average information which is present in this signal. It will give me this information. So now how do I obtain the average value in a given information? So here what happens is, since if you just observe, this is a function of two parameters, that is theta and phi. Therefore, in order to take the summation of all those points, you take double integration of the power pattern. Double integration of the power pattern. Then apart from that, if you just observe, this part is nothing but d omega. D omega. Now we had seen that we assume the antenna at the center and we traverse at a given constant distance around the antenna. So it is that you're traversing around the sphere, what you're considering. So that is, the sphere is having a radius of r, and on that sphere, on the surface of the sphere, you try to measure the power density values. So we are assuming that this is measured over the sphere and we had obtained that this is how it is appearing. That is, say, p of theta comma phi. So this is how the, so this part is giving me what? Summation of all the points related to power density. So here also it is the same thing. You are taking double integration of this factor with respect to what? D omega. So since we have those two angles, we have to consider the beam area related to that. That is a solid angle we have to consider. So now I have to divide it by a factor in order to get the average value. So I have to divide it by what factor? I will divide it by a factor of 4 pi, because a sphere will subtend a maximum angle of 4 pi. So whenever you are traversing, you are assuming an antenna at the center and you are traversing uh, around the surface of the sphere, which is having a radius of r. So if you're traversing around, so this one actually subtends around 4 pi. a solid angle of 4 pi. So you are considering that entire points on that solid angle. So therefore you divide this parameter by 4 pi. So therefore what you have is average power is given by double integration of p of theta comma phi with respect to the solid angle, that is d omega, which is nothing but sine theta d phi divided by 4 pi. So that is what you are specifying over here. So therefore, by definition of directivity, we have directivity is given by P max divided by P average. Now we got to know what is P average from this equation. So I substitute P average in the above equation. What I'll get is P max divided by 1 by 4 pi double integration P of theta comma phi d omega. So now remember, this Pmax value will be constant. It will be just one value what you're considering. So it will be a constant value. So if it is a constant value, what we can do is we can take this parameter in the numerator. When I take this in the numerator, what happens is in the numerator, it will be 1 divided by Pmax. It will be 1 divided by Pmax. So here that simplification we have done. So since this is a constant value, right, I can take this parameter inside the integration. So which will give me this information, that is P of theta comma phi divided by P of theta comma phi, its max value. So I'll be ending up with this equation. And lastly, if I just take 4 pi above, I'll be having directivity equal to 4 pi divided by double integration of normalized power pattern with respect to d omega. This d omega is nothing but it is sine theta d phi. And this double integration is relevant to theta and phi parameters. So now I have got this equation, but what is this denominator equal to? This denominator is nothing but it is nothing but it is the beam area what you had discussed in the previous session. So it is the beam area. So therefore omega A is equal to double integration of normalized power pattern with respect to the solid angle. So therefore what I can do is I can substitute equation 5 in equation 4. So when I do that, what I'll get is directivity in terms of beam area is given as 4 pi divided by omega A. 4 pi divided by omega A. So you can observe that directivity is given, or you can specify that directivity is given as the ratio of the solid angle which is subtended by the sphere, which is 4 pi, to the solid angle or the beam area which is subtended by the antenna which is under consideration. So directivity is given by this equation. Now in a previous session we had discussed regarding what is the maximum angle which is subtended by the radiation pattern relevant to isotropic antenna. So as we had discussed, isotropic antenna is the one which radiates equally in all direction. So when we consider such kind of antenna, what we have that the radiation pattern is spherical in shape for isotropic antenna and circular in 2 dimension. So therefore what happens is the beam area which is subtended by the isotropic antenna is 4 pi. Beam area, that is the omega A, which is subtended by the radiation pattern of the isotropic antenna is 4 pi. So therefore what happens is directivity for isotropic antenna will be 4 pi divided by 4 pi, which is 1. So isotropic antenna has the least directivity. Isotropic antenna has the least directivity. And we had mentioned that any other antenna, isotropic antenna is an ideal antenna. Practically, I don't have antennas which radiates equally in all directions. There will be slight changes. So therefore, what happens is omega A for other antennas will be actually lesser than 4 pi. It will be lesser than 4 pi. So therefore, what happens is this equation, if you just observe, it will be 4 pi divided by a smaller number. 4 pi divided by a smaller number. The highest value which is present is 4 pi. The lowest value possible is theoretically it is 0. So if you just observe, what happens is directivity is in the range of 1 lesser equal to d, and it is lesser than infinity. If I theoretically consider it, this is the range of directivity. This is the range pertaining to directivity. So therefore what happens is directivity of 1 is obtained for isotropic antenna, and practically when you consider directivity is greater than 1 for the other antennas. So that is what we get the information related to directivity of an antenna. Now what is the other parameter what we have to see over here? So here we have just taken an example. Suppose omega A is 2 pi steradians. It is 2 pi steradians. That is 2 pi is the solid angle which is subtended by the radiation pattern due to an antenna which is under consideration. So if I substitute this one in this equation, what I'll get is 4 pi divided by 2 pi, which is gives us the information identifying that it is 2. So what is this indicating is, it is indicating that the antenna which is under consideration is highly directive in one of the directions as compared to that of the isotropic antenna. So for isotropic antenna, the pattern will be circular in 2-dimensional. For example, it might be like this for the other antenna. So if it is in that is radiation pattern is in this form, then this is subtending say 2 pi, this is subtending 4 pi. So when we consider that, what happens is we get to know that the antenna which is under consideration has a directivity of 2. That is based on this parameter. Now I can represent this term into so what we refer to as dBi, which is decibel over isotropic. That is decibels over the isotropic. So in order to obtain that, what we do is whatever value we get, we take 10 log of that value. So when we take 10 log of this value, we get, in this case, we get it around 3.01 dBi. So what is this dBi? So here, since we are measuring this value with respect to the solid angle which is subtended by the sphere, and that radiation pattern is emitted by which antenna? It is by the isotropic antenna. Therefore, the antenna under consideration for reference is the isotropic antenna. So therefore, what we refer is in antennas, whenever we take log of this for the using this equation, we obtain this one. So we specify it as dBi and not just decibels. This is indicating that see 4 pi is due to the isotropic antenna, and this one is due to the antenna which is under consideration. So with reference to the isotropic antenna, we are identifying what is the directivity. So if we are doing this, we when we take 10 log of whatever value is there, we represent this one over the isotropics, decibel over the isotropic. So because the isotropic antenna is the reference point for these antennas. So this is what we have with respect to directivity. So directivity can also be defined in terms of radiation intensity, which is defined in this form. That is, directivity is defined as the ratio of maximum radiation intensity to average radiation intensity. In this case, um is the maximum value of the radiation intensity, and u naught is the average value of radiation intensity. So these are the two different ways of defining the directivity. Then apart from this, we have another term, that is gain. That is a gain of the antenna. So how do I define the gain of the antenna? Gain of the antenna is defined based on the efficiency factor. So gain of an antenna is defined as the product of the directivity with the antenna efficiency factor. Antenna efficiency factor. So here, what you can observe is, we can observe that directivity, we are not considering the overall system efficiency. We are assuming that system is 100% efficient. Therefore, we are obtaining the directivity value. But when we consider the system efficiency, that is the antenna efficiency, we get the gain value for that antenna. And this k, what we are identifying is the antenna efficiency factor, which is generally is in the, it is in the range of 0 to 1, that is 0% to 100%. So if it is 100%, then gain will be equal to directivity, or else gain will be always less than the directivity. So this is with respect to the directivity, as directivity and gain of the antenna. And sometimes gain is also defined as power gain. It is also mentioned as power gain. So next, we had seen that here, if you just observe what we had directivity, which is given by 4 pi divided by omega a. Now in this equation, right, you should remember that if the numerator is 4 pi, omega a, whatever value you are getting, it also should be in steradians. It should be defined in steradians, because it is actually the ratio pertaining to the solid angle which is subtended by the sphere, that is which is the radiation pattern of the isotropic antenna, and this one is the beam solid angle which is subtended by the antenna under consideration. So 4 pi is actually 4 pi steradians. So therefore numerator also should be specified in steradians. Now if you are considering this one in square degrees, if you are considering in square degrees, then you have to convert this also in square degrees. So we had discussed previously, right, that we had discussed previously that 1 steradian is equal to 1 radian square, and this one is equal to 180 divided by pi square. This is square degrees. So this is 1 steradian is equal to these many square degrees. So therefore you can utilize this equation and try to see what is 4 pi steradian equal to. So 4 pi steradian will be how much in terms of square degrees? You use your cross multiplication method, that is 4 pi steradian multiplied with 180 divided by pi its square, this divided by 1, because it is, you are considering like 1 steradian is this value, then 4 pi is how much, that is what you are trying to identify. So when you convert this one, right, this one turns out to be nearly 41,253 square degrees. So 4 pi steradian is nearly equal to 41,253 square degrees. So in some cases, we can see that directivity is also specified as D is equal to 41,253 divided by omega A. Even this equation is also correct, provided this is given in square degrees. So therefore omega A also should be in square degrees. So this is one thing what you have to remember when you're referring to this equation. If you're using 4 pi, this is in steradian, therefore numerator also should be in steradian. If you want to convert it into square degrees, it will be equal to 41253 square degrees divided by omega A, and omega A is also specified in square degrees. Okay. So that is what I have specified over here. That is 41253 is nothing but the steradian converted to square degrees. So now in previous problems, right, we had seen that omega A. So in this case, what we had obtained, omega A is nothing but double integration of normalized power factor with respect to sine theta, d theta, d phi. So this is this parameter what we had, which is nothing but the normalized power factor. So this one gives you the beam area. So if I use this integration, right? If I use this integration and obtain omega A, I'll get directivity as a exact directivity equation. That is omega A. If I substitute it with this equation, that is this integration equation, I'll get exact directivity value. I'll get exact directivity value. But in previous this thing, we had seen that omega A is also given with another factor, that is omega A is product of half power beam width along theta and half power beam width along the phi directions. So we had obtained even this equation. So if I use this equation in this case, right, then I'll get directivity, I'll get approximate directivity. So if I use the exact equation for omega A, I get exact directivity. If I use the approximate equation for omega A, I'll be getting the approx directivity. So these are the two things what we have to look forward. So this one is giving you what? The approximate directivity. If you substitute it with the integration, that is omega A, you will get the exact directivity. So this is what we have for directivity and the gain parameter discussion. So then apart from this, we'll look forward to solve a problem. Okay, we'll consider this problem. We'll not consider the previous one because in the previous problem, right, you require information pertaining to module 2. So when we come to module 2, we'll be discussing this problem. So at present, we'll not be discussing this since we haven't discussed the points which are pertaining to 10 isotropic point sources. So that information is present in the next module. So there we'll discuss regarding this problem. So here, let us consider this problem and try to identify the directivity values. So in this one, what information has been given? So it is specified that you have a normalized field pattern of an antenna which is given by En is equal to sine theta into sine phi, where theta is the zenith or the elevation angle of measured from z axis, and phi is the azimuth angle which is measured along the x axis. Okay. So these are the two parameters what they have given. So if you just represent this, so x, y, z, azimuth angle is measured from the x axis and theta, that is the elevation angle, is measured from the z axis. So if you and the normalized power pattern has the angle which is given in this range. That is, theta is in the range of 0 to pi and phi is also in the range of 0 to pi. So what is he specifying? He's specifying that this power pattern, this field pattern what is given, it is falling, it is having only values in these particular range. That is when theta is 0 to pi and phi is 0 to pi. And for the other values, it is 0. Otherwise, it's 0. So here we have to find what? We have to find the exact directivity, approx directivity, and the dB difference. So as I mentioned, we know that directivity is given by what? Directivity is given by 4 pi divided by omega A. Omega A. If I want to know what is the exact directivity, omega A, I'll be identifying using the exact equation, that is the integration of the normalized power pattern. And if I want the approx directivity, what I'll be doing is I'll be identifying what is theta HP and phi HP for this pattern, and then multiplying those two in order to obtain the omega A value. and I'll use those values in this equation. So I'll be getting what is the approx directivity. And last one we'll check out once we identify these values. So therefore, we have d is equal to 4 pi by omega a. That is, I want to identify the exact directivity. Therefore, what I do is I replace omega a with the integration equation. That is the exact equation. So here integration with respect to theta and phi, the normalized power pattern sine theta d theta d phi. Now remember, here they have given the field pattern. If I want to know the power pattern, I have to take square of this value, that is square of the normalized field pattern. So I'll get to know what is the power pattern. So when I take square of this, what happens is I'll be getting this entire equation, which will be replaced in the numerator. That is integration theta integration phi sine square theta sine square phi into sine theta d phi. So therefore I have sine cube theta into sine square phi with respect to theta and with respect to phi. And what are the limits they have given? They have given the limits for theta and phi in the range of 0 to pi. So we have to substitute that limits in the limits of this integration. So once we substitute this one and simplify this entire parameter, so you can simplify it using the simplified equations, wherein sine square phi is 1 minus cos 2 phi divided by 2, and sine cube theta is 3 sine theta minus sine 3 theta divided by 4. So you can use this equation, and you can simplify this entire equation. When you simplify this, what happens is you will get directivity which is equal to 6. So I am getting directivity equal to 6 by using the exact equation, that is using the integration for omega a. So directivity is 6 for this case. Now, what about the directivity using the approx equation? I want to know what is the approx directivity. In order to do that, what I do is I use omega a as the product of theta hp and phi hp, that is half power beamwidths in the respective directions. So when I do that, so here you can see that in field pattern what is specified. In field pattern it is specified that this pattern is equal to sine theta and sine phi. So therefore here you can here you can see that you have uh, sine theta in the theta plane and sine phi in the phi plane. So therefore both the planes I can separate, and separately I can identify what is theta hp for sine theta and what is theta phi hp for sine phi. That is electric field along the theta direction and electric field along the phi directions. So here again, in order to identify the half power beamwidths, what we have to do is we have to equate this equation equal to 1 by square root of 2, since it is field pattern. So when I equate this one to square root of 2 or 2, what happens is I'll get theta equal to 45 degrees. So therefore, when theta is equal to 45 degrees, what you have obtained is you have obtained along one direction. So therefore, overall half power beamwidth will be twice this theta value. Theta hp will be twice this theta value. Therefore what I'll get is theta hp is equal to 90 degrees. So similarly for the phi direction, that is we have e phi equal to sine phi. You equate this one to 1 by square root of 2, and when you equate this one you get to know that phi for phi equal to 45 degrees, this equation evaluates to 1 by square root of 2. So therefore phi hp will be twice this value, so which is 90 degrees. So therefore you've got to know that theta hp is 90 degrees and phi hp is 90 degrees for the given field pattern. So now what I do is I substitute it in this equation. I substitute this in this equation because we know that it is 4 pi by omega a, where omega a is theta hp into phi hp. Now remember, if these angles are in radians. So this one will be 4 pi. If these angles are in degrees, remember to utilize, you convert that steradians into square degrees. So it is 41253 when these angles are specified in degrees. So here, since these two we have specified in degrees, right? What I do is I make use of the other equation, that is 41253. Or else what you can do is you can do the other way. You can still use 4 pi by omega or 4 pi by theta hp into phi hp, provided you convert this 90 degrees to its radian value, which is nothing but 4 pi, sorry, a pi by 2, and this one is also pi by 2. So both are in radian. So if that is the case, when you consider this, then you can refer to this equation. That is 4 pi by 2 into pi by 2. So, but if you are referring to degrees, right, remember that you have to use here 41253. So when you consider that, you will get directivity which is equal to 5.1, which is approx directivity. Previously you got directivity equal to 6, and in this case you have got directivity equal to 5.1. So previous one was the exact directivity, this one is the approx directivity. Now what is the last part they have mentioned? They have mentioned that you have to obtain the dB difference. It is specified in the problem itself that you have to obtain the dB difference. So what you have to do is, whatever value you have got for exact directivity and approximate directivity, first convert them to dB and take the difference between them. So that is what you have to do. So in order to obtain the dB value, what we have to do is we have to, so if we just take for the exact value, right, in terms of dB, you have to take 10 log of the exact directivity. So which is wherein you will be getting around 7.78 dB, and for approx it is 10 log of approx directivity, which is 7.08. So when you take the difference of this, which it is around zero point 0.7, it is around 0.7. So when you take the difference, right, you have to take the dB difference. They have specified in the problem itself that you should obtain the dB difference. So when I take the difference between these two, it turns around for around 0.7 dB. Now, if you want to know what is the difference in terms of your regular parameters, convert this dB value back to its regular value. So you know that this is equal to 10 log of this delta dB. So when you convert it back, you will get around 1.178. So even if you keep up to this, it is sufficient, since the problem has been asked in terms of dB difference. So take the dB value of 5.1 and 6, that is the exact directivity and approx directivity, and take the difference between them. That will give you the dB difference, which is around 0.7 dB. So this is with respect to directivity. That is problem pertaining to directivity. So now what we'll consider is, we'll consider what happens to the directivity when we know the radiation pattern, how we can identify the directivity when radiation intensity is provided. So now here one example they have specified that a source is with unidirectional cosine power pattern. So this is nothing but they have specified the radiation intensity of the type cosine. That is, the radiation intensity is in the form of cosine. So how do I obtain the representation for this? So in this case, right, what I do is I'll consider, say, if I have the variation. Okay. So here, suppose I'll consider the theta elevation. So I have the theta representation. So it is two-dimensional what I'll be considering. So here we know that at this point it will be 0, at this point it will be 90 degrees. At this point it will be 90 degrees. And I continue. So here, how do I identify what information has been given? So here, remember, it is specified as unidirectional, and it is specified as it is having the form of cosine, that the radiation intensity is in the form of unidirectional and it is in the form of cosine. So now when we consider the theta value, right, we have theta 0 lesser equal to theta lesser equal to pi or the 180 degrees. So theta is actually in this range. But when we specify unidirectional antenna, right, when we specify that it is unidirectional, then what happens is in only one direction I'll be having the radiation present. In the other direction it will be 0. So therefore for unidirectional antenna, right, what happens is theta will be in the range of 0 to 90 degrees. It will be in the range of 0 to 90 degrees. This is for unidirectional antenna. For other antennas, I have to consider this range and obtain the solution. So now, as it is mentioned that the pattern is of the form cos, that is cosine. So now what I do is I'll try to plot the values over here. So what is cos 0? Cos 0 is 1. So this will give me the normalized information. So it will be cos 0 is 1, cos 90 is 0. So if this is a dB plot, right? If this is a dB, if this is a plot in this form, then what happens is this one is giving me the highest value, the lowest circle is giving me a lesser value. So as I move inside, right, I'll be having lesser value of the radiation. So in this case, suppose this is the circle which is representing the radiation pertaining to 1. So here cos of 0 is 1. So that value will fall somewhere here. So when I come to 90, cos of 90, when I substitute over in this equation, what I get is I get 0. So which is identified by this point. So if I come at 45 degrees, for example, if I take at 45 degrees, it is 1 by square root of 2, which is around 0.707. So it might fall somewhere here. So if I take all the values, right, when I consider all the values, this is how the pattern will be appearing, which is nothing but your cos representation. So in your waveform, how you represent it, you represent this in this one in this form, wherein this one is referring to cos 0, this one is referring to cos 90. So that is how we are obtaining it. So when I plot it, it turns around in this form. Now what about this side? Again, it will be like 0 degrees, 10 degrees, 20, 30, 40 and 90 degrees on the other side. So when I plot this side, I'll get a pattern which is in this form. So the radiation pattern will be appearing how? It will be appearing like this. It will be appearing like this. So this is when we are considering unidirectional antenna, and this pattern is in cos representation. It is in the cos form. So here what is happening? So from pi by 2 to pi, from up to, that is here 180 degrees. Why we are not plotting? Because it is specified that it is unidirectional antenna. Therefore, only in one direction I am considering the radiation being present. The other direction there is no radiation. So that is what we have based on this information what is divided. So here it is given as unidirectional and this side it is given as cosine value. So when we consider this, how it will be represented, it will be u is equal to cos theta. So here what we had obtained it in terms of normalized information. So if I multiply this one with u max, so all the values in the normalized pattern, how it will be? It will be u divided by, that is all the normalized values will be u divided by um. So if you take this at the other end, you will get the representation for u. You will get this representation. So therefore, what we do is, I know that in the normalized pattern is cos theta, but I want to represent it in the radiation intensity form. So therefore, I multiply this normalized pattern with Umax value. I'll get the overall radiation intensity pattern. And here the limits are theta is in the range of 0 to pi by 2 and phi will be in the range of 0 to 2 pi. Phi will be in the range of 0 to 2 pi. So this is what is represented over here. So now directivity, I have to identify the directivity for this given pattern. So what is the directivity value for this? Directivity is given as the ratio of the maximum radiation intensity to the average radiation intensity. Now from power theorem, right, we had identified what is the power which is being radiated from an isotropic antenna. That is in this discussion we had. So here we had discussed regarding that using the power theorem when radiation intensity is given. So U naught is the radiation intensity because of the isotropic antenna, and generally in those problems what we do is we consider this value as the average value. This value as the average value for the antenna under consideration. So therefore from this equation what we had obtained, we had seen that the overall power is given by 4 pi U naught. So in this problem, right, what we have done is, in this problem, this equation is because of the power theorem consideration what we have done. So here we are assuming that U naught is the average power radiation intensity which is being radiated by the antenna under consideration. We are assuming that it is equivalent to the radiation intensity which is being emitted by the isotropic antenna. So therefore, I know that the overall power which is being radiated by the antenna under consideration under ideal condition will be equal to 4 pi into U naught. It will be equal to 4 pi into U naught. And now here I got to know that this is the actual pattern which is being radiated by the antenna which is under consideration. So this is ideally the power that has to be radiated. Now when I use the equation, that is the power theorem with respect to this parameter, we have uh, the total power radiated is equal to theta limits and phi limits u into d omega. What is d omega? It is sine theta d phi. So when I replace u, right, I have um into cos theta, that is this parameter. It is into cos theta, which is sine theta d phi. So when I simplify this parameter, right, when I simplify this integration, now here I have to check out the limits. So limits of theta is in the 0 to pi and phi is in the range of 0 to 2 pi. So substitute the limits and simplify this overall equation or the integration. So when we simplify this, what happens is I get power which is equal to pi into pi into So here we got to know that the in terms of the average radiation intensity, the overall power is 4 pi. But when we consider the actual radiation intensity, we get power equal to pi into Now what we do is we equate these two equations, that is equation 4 equal to equation 2. We equate both these two equations. So when we equate both the equations, what we get is, so here we have equated it. So when we equate both the equations, that is pi times um equal to 4 pi times u naught. That is the other equation. We when we simplify it by by u naught, we get a value of 4. So this is nothing but it is the directivity information of the antenna which is under consideration. Okay. So this is the directivity value of the antenna which is under consideration. So here remember what terms we are specifying. It is unidirectional and it is cosine in nature. It is unidirectional and cosine in nature. So therefore, the radiation pattern will be cos theta. So since it is unidirectional, theta will be in the range of 0 to pi by 2 and phi will be in the range of 0 to 2 pi. So unidirectional or bidirectional will be mainly affected by this limits, theta value. So now what you do is we know that from power theorem for an isotropic antenna, power is 4 pi u naught. And in this case, what we are doing is we are considering u naught to be equal to the average radiation intensity of the antenna, which is under consideration. But when I consider this parameter and identify what is the total power which is radiated by the antenna, in this case, we get it equal to pi times therefore, what we do is we equate pi times with 4 pi u naught. That is the equation 2 what we had considered. So when we simplify this one as the ratio of by u naught, I'll get the value of 4, which is nothing but the directivity value of the antenna, that is unidirectional cosine pattern, which is radiating in that form. So this is how I identify the radiation, the directivity when you specify the pattern over there. So now another two problems are there. I'll discuss that and wind this session up. So here we can see that source is having bidirectional cosine pattern. So now I'll not go in depth of how this is represented. So since it is specified that it is bidirectional, so therefore the theta will be in the range of 0 to pi. If it is unidirectional, it is in the range of 0 to pi by 2. In this case, it is bidirectional. So bidirectional in the sense it is having in two directions, it is having the main globes. That is maximum, it is radiating maximum. So therefore, for bidirectional, right, the value of theta is in the range of 0 to pi, and for phi it is in the range of 0 to 2 pi, and the pattern is specified to be cos. So therefore we consider cos theta, and when we multiply it with the value, I get the overall radiation intensity pattern, or the intensity pattern in short. So now again I apply the same concept in order to identify the directivity. That is, I have to identify by u naught, which will give me the directivity value. In order to obtain that, first we consider that the overall power which will be radiated should be equal to 4 pi u naught. So this is ideal situation. It is 4 pi u naught, where u naught is the average intensity value. And the other way of estimating the power is taking double integration u dot d omega. That is, you substitute u with this parameter, that is cos theta. So now when you consider that, what we do is we simplify the equation, and in this case what happens is theta will be in the range of 0 to pi, since it is bidirectional. Previously it was 0 to pi by 2. Now what you do is you have to consider for theta, right, it is a cos theta pattern. If you just consider, that is, when you simplify this cos theta into sin theta, you have a function which is actually even function. So if it is a even function, you can consider this to be 2 times integration of theta is equal to 0 to pi by 2. Now remember, in this case what happens is, if you take theta is equal to 0 to pi, this overall power equation, that is equation 3, will be equating to 0. So just be careful when you are considering bidirectional cosine representation. So in this case, what happens is just convert this limit, since whatever equation we are getting, this one sine theta into cos theta will be sine 2 theta divided by 2. So this one is actually even function. Therefore, what you do is for even function, integration of 0 to pi will reduce to 2 times integration of 0 to pi by 2. Therefore, that reduction is done over here. So once you do the simplification, you solve this integration representation over here, and what you will be having is you will be having power which is given as 2 pi divide 2 pi into um. So now what I do is I equate p is equal to 4 pi u naught equal to this equation, that is 2 pi um. So when I solve it for by u naught, what I get is I get a directivity value of 2. So remember, as I mentioned previously, directivity has to be greater than equal to 1. Now in this integration, right, if you don't change the limits, what happens is this equation reads down to 0. So if it is reading down to 0, that is you are getting 4 pi equal to 0. And when you consider by u naught, what you are getting is you are getting a value of directivities which is wrong. So for this case, directivity is equal to 2. Directivity is equal to 2. So this is the problem pertaining to cosine. So now you can obtain similar in the similar way we can obtain the directivity for sine pattern. So sine power pattern. So when we are not specifying anything, it is considered that it is bidirectional. Therefore, you have u is equal to sine theta. This is indicating that the pattern is sinusoidal in nature. Sometimes it is also termed as donut shaped. Yesterday we had seen one example, right? So it will be in donut shape in 3-dimensional. So if they specify this, it is mentioned that it is a sine pattern, and when you multiply this one with the you will get the overall intensity pattern. So considering this, you try to obtain the directivity. So you take this, you double integrate this intensity with respect to theta and phi, you will get the p value, that is in this case it is pi square into and from power theorem we know that p is equal to 4 pi u naught. So we equate both these equations, and in this case what we get a directivity of 1.27. So these are the few problems pertaining to directivity. Okay.